Hello.
Today we are going to show you how to do a double pendulum. DIY!
We will go through the steps in order and hopefully you'll learn how to do this yourself.
So, step 1.
Define the system.
So the system that we are going to be doing is a double pendulum the way that Taya is drawing right now. So it will consist of two pendula hanging from a single support with the second pendula hanging from the first pendula. We will also be defining our system using generalized coordinates. So instead of caring about the angles of the pendula relative to the first support, we're caring about the angles of the pendula relative to each other. That's not all we need. We also need to draw some free body diagrams. And here's an important reminder that free body diagrams must be free. Wow, they're so free. Okay, so Taya, can you tell us a bit about those forces that you're drawing?
So we have gravity, we have the tension of string 2, and we have the tension of string 1. Now M2, hanging down here, will only have gravity and the tension of string 2. However, when we see these things, it is very difficult to know what is going on with these tensions over here.
This system is disgusting.
And when we solve this problem, we don't care about them.
Nope, not at all. What do we care about, Taya?
We care about the energies. So we will go on to the next step. So step 2 is to define the system in terms of Lagrangian mechanics. So instead of understanding what the constraint forces are, we don't care about them. Constraint forces don't matter with Lagrangian mechanics. All you do is you take the kinetic energy of the system minus the potential energy of the system.
And what you do with those is you use calculus of variations to find the stationary path of the system. To explain kind of what that means, take for example a person who is standing under some trees in the rain. They want to get to this door here, which is underneath all of the shelter. There are a couple of different paths that they can take. So they can walk directly to the door, but that gets them soaking wet because it's raining. They could walk straight to the building and then all the way over to the door, but nobody wants to do that because people are lazy. So instead what the person does is they determine their own best stationary path where they walk a little bit longer overall, but more of that time is spent underneath the shelter.
In order to understand how to make the stationary path work, so this integral 0, you use the Euler-Lagrange equation, which is dl, so your Lagrangian partial derivative with respect to x. You take the partial derivative with respect to x dot, so your velocity, and then you take the time derivative of what you took with respect to your velocity. Now we have to write the energies in terms of the Lagrangian, so we can write our system in terms of L equals T minus U.
And all we need to do that is find the kinetic energy of each of the masses and add them together, as well as the potential energy of each of the masses, and add those together to find the totals for the system.
Remember, this part is a little bit tricky because you have to take into account the interactions between some of the masses. So you don't want to double count, but you also need to make sure that all of the interactions are accounted for.
So that is what we will be doing right now. Boom, boom.
Now we will take the partial derivatives. Here we're there's actually going to be two different equations because you have theta 1 and theta 2. So your thing will have two different Euler-Lagrange equations.
Many hours later and many sign errors later, you will eventually find that theta 1 double dot comes out to be this marvelous beast right here, and theta 2 double dot comes out to be this. Now, looking at these, you can't see what the motion of the system is. At least I don't think you can. If you can, that's wow. But if you're like us and really want to see what it does, you can use Python to see what the motion looks like.
So write your Python equation, write your Python code, two equations of motion, boom, you got a simulation, which we will show now. So you can see our double pendulum system working. You have kinetic energy with the yellow line, potential energy with the blue line, and the red line is the total energy of the system.
And you will see that our system is consistent with what would physically happen in the real world because energy is conserved.
And once you complete all of these steps, you should find
It works!